In this presentation, we will go through some basic information about resistivity that is important to keep in mind if you are going to be interpreting controlled source electromagnetic data. We will start by looking at some basics of sediment resistivity, also resistivity anisotropy and resistivity measurements, particularly well logs. And finally, we go through reservoir resistivity and some pitfalls in reservoir resistivity assessment. Let's start with sediment resistivity. Sediment is eventually the mixture of several materials. Some of them have a very high resistivity. Actually, most of them have very high resistivity here on the right. And then we have brine that is much lower resistivity than the others. One of the important things to notice here is that in the horizontal axis here is resistivity in a log scale. So you should notice that there are many orders of magnitude of different values between the brine resistivity and all the other highly resistive stuff. So what will drive an electric current in sediment will be the brine, because everything else just doesn't conduct electricity at all. So when we put together sediments, they end up somewhere in between the brine properties and all the highly resistive stuff. How close they are to the brine properties depends on basically how much brine they have. So it's typically a function of porosity. All relationships that explain sediment resistivity do so by taking into account the properties of the brine, because you can see here brine actually itself spans quite a wide range of values. So in order to figure out sediment resistivity, you need to take into account the properties of the brine and the amount of brine in the sediment. So here is one of those relationships that explain sediment resistivity, and almost all of them do so by relating the sediment resistivity to the resistivity of the brine, taking into account the amount of brine in the sediment. So these two factors center, one is the porosity, the other is the water saturation. Gustavus Archie, in the first half of the 20th century, created these plots. He had some measurements of porosity versus resistivity, and he plotted them in a log-log scale using what's called here the resistivity factor, which is the ratio between the rock resistivity and the brine resistivity. And he obtained these sort of clouds of points, and the slope of this linear relationship is exponents out here are the slope of these lines out here. So those are the exponents here. Every other resistivity relationship that explains sediment resistivity works very much like this, trying to explain the relationship between the porosity, the amount of brine in the sediment, and the properties of the brine to the rock resistivity. Now let's move to resistivity anisotropy. So if we go back to our high school physics and electric circuits, if you have resistances in series, such as these ones out here, and you wanted to find the total resistance, you had to sum them up. This is of course dominated by high resistances, because any current flowing through this system must flow through all the resistances, and if one of them is very strong, then that means the total resistance has to be very high. For resistances in parallel, the total resistance is calculated through the addition of the inverse resistances. That means you have to add conductance. And this is of course dominated by low resistances. If any of this is very low, most of the current will go through that resistance. Now, if we are considering a layering, very similar principles apply. So if you're trying to flow a current normal to the layering like this, that current must flow through all the different layers. And the average resistivity of those layers, which is what we're interested in, because now we're interested in resistivities rather than resistances, the resistivity will be the average, the arithmetic average resistivity of all of the components. Now, if you try to flow a current parallel to the layering, the resistivity, this is similar to this case out here, and instead of calculating the arithmetic average, you have to calculate the harmonic average, which is of course driven by the low value of resistivity. If you recall from previous slides, one of the characteristics of earth materials is that they have a really large range of variation of resistivity values. And very large contrasts, of course, will generate very big difference between the arithmetic average and the harmonic average. And this translates into very high expected anisotropies, which is what we typically observe in CSEM imaging. Here is one example from the North Sea. The values up here, these are the ratio of the resistivity normal to the bedding to the resistivity parallel to the bedding. What you can see is that you have values of about 1 in the water, and very quickly when you get into the sediment, you have very quickly values of around 2 or even 4 out here, or actually higher than 5 below the top Cretaceous here. If you compare this with typical seismic anisotropy values, seismic velocity anisotropy values, you often have that one of the components, the horizontal component, let's say, of the velocity is 5, 10, 20% higher than the vertical. Now, that means that if you turn into the same sort of scale, all seismic anisotropies will typically sit down here in the lower part of the color scale. So resistivity anisotropy, the Earth in terms of resistivity is much more anisotropic, at least in sedimentary basins, it's much more anisotropic than in terms of velocity. Let's look into well log resistivity measurement. If we had a layering like this on the right, you know that in terms of resistivity, we have large anisotropies. And the bed parallel and bed perpendicular components are very different, with the bed perpendicular being higher. Most wells are drilled perpendicular to the layering, such as this one that we have here. And most resistivity well logs will be induction logs or lateral logs. Lateral logs induce a current radially away from the borehole, and induction logs induce a current circularly around the borehole. But both of them are then measuring resistivity parallel to the layering, which means they will mostly overweight the low values of resistivity. Now, there are a couple of situations where this will not happen. Most of the time, it will be due to the geometrical configuration not being exactly this. So in a situation where you have high inclination boreholes or steeply dipping layers, the induction and lateral log will not measure just the harmonic average, but they will measure something in between the harmonic average and the arithmetic average in those situations. Also, you could have a triaxial tool available that measures the full resistivity tensor. But most of the time, your borehole will be more or less perpendicular to your layers, and you will have either lateral log or induction logs available, which measure the harmonic average. And this is a problem because the harmonic average is driven by the low values, while we are interested in the reservoir, which is supposed to be the high values of the resistivity. Let's see how that works in a bit more detail. Here we have the blue lines are the actual resistivity model, so that's what we would like to measure. And the orange lines is what the well logs would measure in each one of these cases. And what we have is that there is an increasing thickness of the resistive layers from left to right. Even in the relatively thick reservoir case to the right, the peak here in the well log is actually quite a bit off. So there is an underestimation of the resistivity, and it gets worse with decreasing reservoir or high resistivity layer thickness. And this is, of course, depends on the well log resolution. For deep resistivity logs, which are the ones that you're mostly interested in, this effect starts happening typically at 4 to 6 feet layer thickness. Any layer at that thickness or below will be underestimated. To find out exactly how much thickness, where does that underestimation starts happening, you need to talk to your petrophysicist. Now let's look at reservoir resistivity. If we go back to the basics of sediment resistivity, we had that sediment resistivity is the resistivity of the brine corrected by the amount of brine in the sediment. So you have to have porosity and water saturation in the sediment. The key to understanding reservoir resistivity is going to be understanding the water saturation here. So we're going to look a bit more into water saturation now. Now, at time of deposition, all reservoirs or most reservoirs are actually filled with water. And at a later stage, hydrocarbons are floating and they float and displace. They have to displace the water in the reservoir. And that means you have to find the balance between the buoyancy of the hydrocarbon, density contrast and the column height, and the capillary pressure holding the water in place. And this leads to the sort of drainage curves that you see here on the right, where you see the amount of hydrocarbon that can be essentially pushed into the reservoir depends on the difference in pressure between the hydrocarbon and the water, and that's down to column. The efficiency of this process depends on essentially just one parameter, which is the permeability. You can see here that high permeability reservoirs have a very efficient fluid substitution, and that means you can achieve relatively high saturations with relatively low pressures. And for low permeability reservoirs, of course, it takes much more force essentially to remove water from the reservoir, and that means you need more pressure to achieve similar saturations of hydrocarbon, and you will typically not end up being able to remove as much water. So this number here, this distance here, which is the irreducible water saturation, is typically lower for high permeability reservoirs and higher for low permeability reservoirs, and that means you can't quite remove a lot of water from low permeability reservoirs. They keep a lot of water in the pore space because the water can't move. Now this leads to one simple effect, one translation. How does this translate to resistivity? It's very much like what you see here. These drainage curves here, which are essentially saturation versus pressure, can be easily translated into resistivity. So the saturation turns into resistivity if you assume certain porosities and water resistivities, and the pressure turns into column height if you know the density of the water and the density of the hydrocarbon. And what you see here is just a model, but it's explaining clearly that for low permeability reservoirs, you build resistivity slowly, and actually you build resistivity to relatively low values. And the maximum value here is essentially an indication of the irreducible water saturation. And for high permeability reservoirs, you build resistivity fast in a short column, and actually you build resistivity to pretty large values of resistivity. High permeability reservoirs tend to have very high resistivity. So in the end, for a hydrocarbon charged reservoir, the resistivity of the reservoir is an indication of the permeability of the reservoir. And now some pitfalls in reservoir resistivity assessment. By now you're probably familiar with this sort of CSEM sensitivity plot that shows that for a given target, CSEM sensitivity depends on the area on the one hand and the thickness resistivity contrast of the target on the other hand. Most of the time, exploration teams will have some estimates of thickness and area, but hardly ever will they have estimates of resistivity that they expect for a certain prospect. And we have seen people resort to some problematic methods to obtain a reservoir resistivity estimate. These are using a thin resistivity, a thin reservoir analog, using the average saturation and porosity from the prospect evaluation and put that straight into Archie, trying to get a resistivity like that. And the other is using a small discovery. Let's see how these can be problematic. So let's start with using a thin reservoir analog. Now, as we saw before, if you have a thin reservoir analog, the problem is most of the time your logs will be from a vertical well drilled perpendicular to the layers, and most of the logs will be induction or lateral logs, so you will not have a triaxial log available. The problem in that situation is that the true resistivity models here in blue are typically underestimated by the log response. And even in relatively thick cases like this, which is in the edge of resolution, so as long as you are below the well log resolution, your well log will provide you with an underestimation of the true resistivity. And this underestimation can be really severe. So in a case like this, the log is pretty close to resolution. The peak in the log reads probably around 13 ohm meters, and the true resistivity value here is around 20. So it's not a very severe underestimation. But the problem is, in these sort of situations, the log has lost sensitivity to the high resistivity values. So you could increase this true resistivity value to, let's say, 2000 ohm meters, and the well log would hardly change. Therefore, in reservoir case, the well log measurement typically leaves you with a big uncertainty, which is, well, the true resistivity is higher than the peak. And that's not a lot to go by. So you really need to work on your reservoir model to figure out the true resistivity of your reservoir. You cannot really take the log at face value if you are relatively close to your well log resolution. Now, the second pitfall was using average saturation and porosity from the prospect evaluation to calculate reservoir resistivity. So you can very easily see how this is tempting. You have a relationship like Archie, where all you need is porosity and water saturation and an estimate of water resistivity to actually come up with a reservoir resistivity estimate. But Archie is a relationship that's valid in constant saturation rocks. So it's very good for plugs, something that's plug scale, that's constant saturation. But as we saw before, constant saturation doesn't really happen. In most cases, what we will have, almost every field will have some height to it, and that means close to the contact, the pressure is very low, and higher from the contact, the pressure is increased, and therefore your saturations are going to be increasing. So you don't really ever have a constant saturation, right? That doesn't really happen. What you will always have is a distribution of saturations. Let's say that your average saturation is 60% in your prospect evaluation. That doesn't mean that all reservoir is expected to be 60%, but that the average saturation is 60%. So there will be parts that are higher than 60 and parts that are, or your reservoir that are lower than 60. And typically they will come up all the way from 0 up to relatively high numbers. So if we create a probability distribution with all the saturation values in our reservoir, we get something like this. And most of our real reservoirs will look more like the red curve here with relatively large width or standard deviation than the blue one. The blue one is what you're basically assuming if you apply Archie straight with your average saturation and average porosity. Actually, the impact of the width of the distribution is very, very high. So I want to show you what's the impact of the width of that distribution by calculating in Monte Carlo, having reservoir models with different average saturations and different width of the distribution. And what you get is this. This is the average hydrocarbon saturation in the horizontal axis. In the vertical axis, it's the average resistivity. And in the color scale here is the standard deviation of the saturation. So true reservoirs have a standard deviation around here, around 0.25, 0.2, 0.3, something like that. Now, if you apply the average saturation and the average porosity to Archie, what you're assuming is that you are down here. So that there is no standard deviation, that all of your reservoir is exactly 60% saturation or whatever it is that you are estimating. Now let's look at the difference that this makes in the average resistivity. So if you take 60% here and take 0 standard deviation, so you assume all the reservoir is 60% saturation, you would be calculating that your average resistivity is around 13 ohm meters. Now, the moment you take into account that actually the standard deviation is basically much higher than 0, it's significantly higher than that, so most of your good values are going to be in the orange and red here. Actually, your true resistivity, the true resistivity that you would expect for a reservoir that's actually 60% hydrocarbon saturation, is the same average, but different standard deviation. Actually, it contains a much higher value here of average resistivity. So your expectation goes up by essentially an order of magnitude. You're an order of magnitude off because you forgot about the width of your distribution by assuming it's a constant. And constant saturation reservoirs don't actually exist. So don't use that. Don't forget about the width of your distribution. Take that into account, and then you will have a more reasonable reservoir resistivity estimate, because there is a really big gap here. Now, third, the problem with using a small discovery. So the problem with small discoveries is that they are really abundant. You always have some small bit of reservoir somewhere. And almost by definition, the problem with small discoveries is that almost all of them contain a very short column. So you're always in this sort of environment with very, very short columns. Now, as we saw before, saturations build up with height. So almost never this sort of saturation will be representative of the full saturation that you will have if you have a larger discovery with a larger column. So let me give you one example. In this case, here we have a resistivity log with a fluid contact around here. So there's a contact there. This is a gas water contact. The resistivity measurement peaks at around 7 ohm meters here. Now, is 7 ohm meters representative of what this reservoir would have if we had a larger column? Well, clearly not, because we are essentially measuring a transition zone. In order to estimate what kind of resistivities we would have if we had a larger column, we would need to compensate, we would need to build a saturation versus height function to see where those resistivities would go. And we can build one like this. We take an analog and we create a saturation versus pressure function, and then we turn that into resistivity versus height. And the resistivity versus height function like this one would very well explain the 7 ohm meters that we measure here, about 3 or 4 meters above the contact. And it would tell us that if we were expecting a different column, let's say something in the order of 30 meters or 40, something like this. So if we had a larger column, if we were expecting a larger column, this same reservoir would have more in the order of several tens of ohm meters, or 30, 40, 50 ohm meters, rather than the 7 we were measuring down here with the small column. So be careful when you have reservoirs that have been measured very close to the contact, because most of the time those resistivities will not be very meaningful for the resistivity that you can encounter in a prospect if the prospect contains larger columns. And that is all. Thanks for your attention, and leave any comments or doubts in the comment section below.